Hi, I'm Changyuan Lin, a master's student from the University of Alberta. I'm going to present our paper, Modeling and Optimization of Performance and Cost of Serverless Applications, which is published in IEEE Transactions on Parallel and Distributed Systems. This work has been done in the Performance and Available Computing Systems Lab, or PACS, at the York University. The co-author is Dr. Hamza Kazai, which is also my supervisor. Before getting into the details, let me provide some background information about Function as a Service and the serverless paradigm. Function as a Service, or FaaS, is a new paradigm in cloud computing, which allows you to host and execute functions on the cloud. The function is basically a chunk of code that abstracts a part of an application implementing the business logic. Many public cloud service providers have launched their FaaS platforms, such as IBM Cloud Functions, AWS Lambda, Google Cloud Functions, and Azure Functions. The function is running in an ephemeral isolated environment, and such an environment is usually provided by lightweight virtualization techniques, such as Docker and unikernels. Those FaaS providers take over most operational responsibilities, so that developers can mainly focus on the function source code. And the FaaS platform also handles autoscaling, routing, and monitoring. The function containers can autoscale in response to the volume of requests. So the overhead of server management, monitoring, failover, and scaling is eliminated. Like there are no servers to manage at all, so we could refer to FaaS functions as serverless functions or serverless computing. So developers have easy but somehow limited control over resources allocated to functions. Basically, for each function, developers can just change the allocated memory size and the provisioning concurrency level. All other computing resources, including CPU power, disk I/O, and network throughput, are generally in proportion to the allocated memory size. Another thing is that FaaS providers introduce a new pay-as-you-go billing model, which is based on the function execution duration, memory size, and the number of requests. For example, AWS Lambda charges 20 cents per 1 million requests, unlike 0.00016 for every gigabyte of memory allocated to the function, and the second of the function execution duration. So as just mentioned, we can change the allocated memory size of the function, and all other resources are changed proportionally. So the memory size elects the tuner to control the response time and the cost of the function. And when we change the memory size from the smallest possible value to the biggest possible value, we can actually get a performance and cost versus memory curve, which shows the response time and the cost of the function under different memory configurations. And when we chain together FaaS functions through some communication protocols, such as message queue or HTTP request, we can have a serverless application. The application is serverless, since every function in it is serverless. So here come our motivations. The unpredictable performance and cost of serverless applications, and the trade-off between performance and cost of serverless applications. So when we have a serverless application composed of many serverless functions, to get its end-to-end response time and the average cost can be very tricky because you have to deploy the application on the cloud and perform tests, which are time-consuming and very expensive. And sometimes developers may want to have a performance constraint and a budget constraint. Let's say I don't want to spend more than $50, but I can't accept my application response time is longer than 400 milliseconds either. So we have to find an appropriate memory size for each function in the application to satisfy these demands. And for the whole application, there might be millions of different memory configurations. It is practically and financially unfeasible to test all configurations. So we translate these two motivations into our two research questions. RQ1, can we obtain the end-to-end response time and the cost of a serverless application when orchestration and configuration of the application are given? And RQ2, can we calculate the best performance under a given budget or the minimum cost for desired performance for a serverless application? To solve the first RQ, we propose the performance and cost models, which can get end-to-end response time and cost of a given application and configuration. And we propose the performance and cost optimization algorithms to solve this second RQ, which can give the optimized memory configuration of functions to meet the constraint. So here is an overview of our methodology. Our work basically has three parts: the function performance profiling part, the performance and cost optimization algorithms, and of course, the performance and cost models. They can deliver three outcomes: the performance cost versus memory curve of serverless functions, the satisfying memory configurations to meet the performance and budget constraints, and of course, end-to-end response time and average cost for a given configuration. We first construct the serverless workflow of a serverless application, which is defined as a weighted directed graph. The elements are vertices representing functions, edges abstracting interactions among functions, transition probabilities, interaction delays, memory size, response time, interim response time and probabilities, number of invocations, and the cost of functions. We also define four types of structures in the serverless workflow, which are parallel, branch, cycle, and self-loop. Parallel basically means two or more functions or paths are executed in parallel, and the parallel is completed only after all functions are executed. In branches, the function invocation is conditional, and only one function or path will be executed based on the satisfied condition. Cycle basically means the application jumps back and executes a function again, and self-loops is a cycle with only one function. So with different methods for different structures, the performance models trim the graph by removing, adding, and modifying vertices, edges, and elements, and converts the graph into a probabilistic DAG. For example, to process the parallel, we just return the path with the longest delay and trim off all other parallel paths. For branches, we calculate the weighted average and return the probabilities and response time in each case using an interim attribute RTTP. Then replace the branch with just one vertex. For cycles and self-loops, we calculate the expected number of iterations, modify the response time of the vertex correspondingly, and remove the cycle edge. This is the pseudocode of the performance model. The algorithm finds the structure based on our definitions and then process each structure, convert the graph into a probabilistic DAG, and calculate the end-to-end response time using this equation. For the cost model, we use this equation to calculate the cost of each function in the serverless application. The cost model will use similar methods to remove cycles and loops from the graph, convert the workflow into a delooped graph, and then calculate the average cost of the whole application. So this is the pseudocode of the cost model. This part is to process cycles and loops, and this part is to calculate the cost of the application. Well, that's pretty much about the performance and cost models. Now let's talk about the performance and cost optimization algorithms. The trade-off between performance and cost serverless applications can be broken down into two optimization problems actually. The best performance under budget constraint problem, or BPBC problem, and the best cost under the performance constraint problem, or BCPC problem. The BPBC problem is to find a memory configuration that achieves the minimum average end-to-end response time of the application, with the average cost less than or equal to the budget constraint. On the other hand, the BCPC problem is to find a configuration that achieves the minimum average cost while keeping the average end-to-end response time less than or equal to the performance constraint. We proved that BPBC and BCPC problems are fundamentally more complex variants of the multiple choice knapsack problem, aka MCKP. In MCKP, we have a backpack with a capacity, for example, 16 kilograms, and we have to put exactly one atom from each group into the backpack. Each atom has a weight and a value. Our goal is to find the atoms to pick that can maximize their values within the capacity of the backpack. So in BC and BCPC problems, three groups of atoms are equivalent to three serverless functions in the application, and for each function, we have to choose one memory configuration that is associated with a response time and cost. Our goal is to find the memory configurations for all functions that can minimize the cost within the performance constraint or minimize the response time within the budget constraint. As MCKP is a well-known NP-complete problem, so BPBC and BCPC are also NP-complete, and we have to use heuristic algorithm to solve these problems. We propose a heuristic algorithm named Probability Refined Critical Path Algorithm, or PRCP, to solve BPBC and BCPC problems. PRCP refines the transition probabilities of edges and simple path as well as the weight of simple path based on the transition probability, and leverages a weighted-based definition of the critical path. It also recursively optimizes the memory of functions on the critical path using a gradient manner and obtains the best performance or the best memory configuration satisfying the constraint. PRCP shares some similarities with the critical path method, but has a different underlying nature. PRCP defines the critical path based on the weight considering the transition probability and the number of invocations. PRCP also has 4 graded strategies to avoid the local optimization. So in the PRCP algorithm, we define the weight of a simple path as this equation, with the consideration of the response time, transition probability, and the number of invocations. And for each path in the workflow, we calculate the weight. The path with the largest weight is the most critical path, and conversely, the one with the least weight is of course the least critical path. In the BCPC problem, the input are the performance constraint and the serverless workflow. PRCP first initializes the workflow by employing the minimum memory configuration for each function in the workflow. In this way, the workflow has the largest end-to-end response time. And then PRCP recursively finds the critical path and calculates the end-to-end response time decrease and cost increase under all possible allocated memory sets of all functions in the critical path. If there are functions and memory sets options that can reduce the cost without increasing end-to-end response time, we choose the configuration resulting in the largest cost decrease. If not, we just choose the configuration achieving the largest end-to-end response time decrease within the budget constraint. If there is no feasible memory sets option within the tth critical path where t is initialized as 1, PRCP will find the t+1th critical path in the next iteration and so on. The iteration ends when there is no feasible memory sets option even in the least critical path with the current surplus. The procedures are similar for solving the BCPC problem, but the PRCP algorithm starts with the maximum memory size and the least critical path, and tries to decrease the response time and increase the cost. The code in the box, which tries to minimize the response time increase or cost increase, is the graded strategy of the PRCP algorithm. We actually designed 4 graded strategies. Let's move back to the performance and cost versus memory curve of serverless functions. We can find that there are a sensitive zone and an insensitive zone. In the sensitive zone, when we increase the memory size, the response time drops dramatically. But in the insensitive zone, the larger memory size does not positively affect the performance that much. However, the cost surges. So it is unwise to increase the memory size outside the sensitive zone. Therefore, to avoid bad optimization solutions, we introduce the benefit-cost ratio, or BCR, into our graded strategies. Instead of arbitrarily maximizing the response time reduction, the strategy is to find the configuration achieving the optimal BCR. So in other words, the idea is to find the configuration leading to the optimal benefit for its cost. For the BPBC problem, strategies are max end-to-end response time over cost and function response time over memory size. For the BCPC problem, the strategies are actually the multiplicative inverse of those strategies for the BPBC problem. This table summarizes all BCR strategies. The name of this strategy basically comes from how we define the benefit-cost ratio. For example, the BCR for the ERT over C strategy is defined as the ratio between the change in the end-to-end response time and the change in the cost, which is basically this equation. So here come our experimental evaluations. For the performance and cost models, we deploy 5 applications composed of 8 to 16 functions on AWS. We use combinations of CPU-intensive, disk-intensive, and network-intensive functions. Both the average end-to-end response time and cost derived by our performance and cost models are very close to the real values reported by AWS. The average accuracy for both models is over 98%. We evaluate the performance and cost optimization algorithms by an application with 6 functions. This is the application workflow, and this is the performance profile of 6 functions. The accuracy for the PRCP algorithm solving BPPC and BCPC problems is over 97% and 99% respectively. So these evaluation results demonstrate our performance and cost models and optimization algorithms can precisely predict the performance and cost of the serverless application and give the optimal memory configurations, satisfying the performance and budget constraints. So all our artifacts are available on GitHub. Please check out. You can also reach me and find my other research projects on my website. That's pretty much it. Thanks for listening.